So this is how close it gets. I'll show more data along that line. So this is the Fermi energy 0. It's below. It's a gap. It's also known from optics. One can do optical conductivity and see it's a gap. It was done by Russians in the 80s, in the 70s or 80s. Okay. But that does not mean that there is no impurity or other things. You can have other things spinning the Fermi level and stuff. And now that we have a detailed map of the three-dimensional band structure, I can use that internal detail to fine align the Fermi surface with the Briand zone, because our experimental precision alignment is not that great as we would love to. And this is often not done in high TC or other compounds, because there people don't really go through those details. So in this case, we're lucky that we had to go through those details and we can fine align. So that gives us more confidence that we're in a position to think about its topological its geometrical or topological behavior. Okay. So typically, now let's get back to everyday intuition that I get surface state when I have a bulk system. I have a 3D I have a system, and then I impose a boundary condition. So then the states at the boundary, they are modified, but they should have some sort of memory of the bulk wave function. It's somewhat distorted or something will happen. So is there a way to connect that? So that is what I'm trying to ask here. If I take cuts on this Fermi surface and look down at higher binding energies, we can always see these linear bands. First time we saw this thing, we thought this system is like graphene, electron-doped graphene, because you have some electron on this Dirac cone, but then we figured it's totally different. Now one can see that the fact that it has bulk linear-like bands, when you impose a boundary condition of some sort, the surface state, whatever you get, it's unusual if you look at this just Fermi surface alone. But the band structure, it looks like it is coming from the bulk band by imposing boundary condition, because it's all linear. And the bulk bands are linear. Okay. Actually, when we did that experiment, we did not know about Z2 physics. We were doing that in connection to thermoelectric compounds, because this is thermoelectric and we wanted to look at a conventional. So then we found this. And we were frustrated because we cannot get rid of the surface state no matter what we do that. So then we found that there are a strange type of surface state that you really cannot get rid of. I had a fight with some LDA band theorists that the cobalt at work. So I really extensively studied what goes on with the surface. Okay, so then we learned that there are certain insulators, band insulator, this stuff is band insulator, where you can form surface states that threads the gap, that are connected, that they connect the conduction and bulk and the valence and conduction band. But most surface states do not do that, and actually one can look up in the literature, most surface states are like that. You can find multiple crossings. So it's like typical in-gap state when you put some impurity or other stuff in a semiconductor insulator. So there's even number of crossing, there's odd number of crossing, and but you have to look at the specific momenta, this time reversal invariant momenta. So then if we do the same analysis, in our case, it's gamma and m, the time reversal invariant momenta of the system, and we count how many states are there, down there, and we see there are 5 states. And how do I know that this is, because the theory requires time reversal invariance. I haven't proved that this is holding, so at least I know that at the Kramer's point, the states are degenerate, and there is a Dirac point there. It's degenerate with the bulk. That's why imaging both at the same time is difficult for us, but you can See that if you extrapolate, this is another Kramers point. So at least despite disorder and other things, the Kramers point is not broken. So that's very exciting, that the Kramers point is intact. And later I will show how to break the Kramers point, and you'll see there's a gap opening. We did actually that on bismuth selenide, not on this compound. Okay. And of course there is correspondence between this band structure and the Fermi surface I showed previously. It's detailed in the supplementary information of our paper. And one can see that if I look, this intensity is always low compared to this part. If I look near here, it's kind of distorted. And not only that, it's not a sharp Fermi surface like this one. And this is, and then there is a lot of intensity out there. And this intensity is K independent. No matter what K you are, this intensity is there. In other words, the Fermi contrast is low. And that is the signature of disorder. There are always states, finite density of states at the Fermi level. And that's why it should be black. It should be like that. And this plot is different. I'm not plotting the EDCs. I'm plotting the second derivative to track the line of the peaks that track. The real data is like that. So there's alloying disorder there. Okay. So then we just find odd number of states between two Kramers point, and we need more evidence that, although in theory, Z2 theory, that should be enough. If we can prove that the states are singly degenerate, if they're doubly degenerate, then the 5 would double into 10, and then there is no Berry phase. How do I prove that the states are single degenerate and there is a Berry phase on the surface? So that's a critical step. Okay. To do that, we have to do a spin resolve measurement and see whether the states are degenerate or not. So this is some raw data, very raw data on a compound that's not ideal. Later on I'll show more ideal, better compound. I'm just showing that for historical reason. This is where we first realized it's single degenerate. So these are my surface states, and I'm doing the same thing. I'm using Mott polarimetry, extrinsic spin Hall effect, to isolate the spin degrees of freedom. So what I do, I take a cut, say at 25 millivolts, where I have large intensity along Kx, and okay, so let me first focus on this one. I'll get to that. So if I separate the spins through the Mott detector, then I see that this band, it ends up in the right channel in my detector, which I call up arbitrarily. And then this guy, this ends up in the blue curve. It ends up in the down channel in the left detector. So this point and this point, they're in two different separate detectors. So K plus and K minus spin maps into, K plus spin up maps into K minus spin down. So this is another proof that despite alloying disorder, time reversal symmetry is there. Okay, so then what I do, I look at the spin of this channel, this crossing. This ends up in the left channel, down. And this signal is weak, but you can see that compared to the red curve, there is something there. This is also in the same channel. So this is spin down, this is spin down. Okay? This is a better set of curves. Crossing one, this is one, is blue, 2 is red. And then 2 and 3 have same polarization. It ends up in the same detector. So what does that imply?
So I have a problem with this assigning the spin. See, the difference is tiny compared to the total.
Right.
So it looks like maybe 5% more.
Yeah, but here that's in this set of curves. Here it's not. Its difference is large. These are also raw data. here the difference is large. If you take the difference between blue and red, it does not fall onto each other.
It looks like 10%.
Yeah. Well, I mean, it also has the. It's not. It's.
So I would like to say. So why there's so much mixing?
Oh, this also has to do with the detector background and inefficiency. It's not theoretical thing. These are the right.
You guys
so the surface state and momentum K, let's say, is not a spin eigenstate.
Yeah.
So
No, that is a separate issue. In a spin orbit coupled system, spin is not a quantum number. I mean, it's not a valid quantum number. So you don't, even on the theoretical ground, you don't expect.
How much?
So that is, I haven't calculated that.
5%.
Can be calculated.
Yeah.
So then you mentioned it can be calculated.
Yeah.
Order one. I mean, it's
It's
not much smaller than one.
Yeah. Therefore.
1 is 100%.
Yeah.
Yeah, but this is smart scattering, right? So
Yeah.
even if it's 100% polarized, you don't.
Yeah, this is the Sherman function is.
Because of the Mott.
Yeah, it's not scattering. It's not.
Okay.
That's what I meant by you already have a background to start with. There should be nothing there, but there is a lot of intensity there.
How selective can your detector be?
Huh?
How selective can your detector be? How much more do you get to one cell and the other? Could be split polarized equally.
So I'll show that in an antimony where the system is cleaner. Okay. So now I can start assigning that 1 is down, 2 is up, and then 3 is up, and there are other stuff, right? So one might guess that since 2 and 3 are up, they should connect above the Fermi level. In other words, right away I know that 2 and 3 are trivial states. They don't carry a topological quantum number. And there is a simple way to check that the spin assignment is correct. All you do, dope the surface. If you put electrons on the surface, Fermi level rises, and you do see that they connect up. So I know right away, out of the 5 surface states, I got rid of 2. I'm left with 3.
Only went out to the surface?
Well, I mean, it will go a little bit in the, it's not just monolayer.
How do you do it?
Just deposit thermal evaporation. Yeah. I mean, I'll show more of that stuff. Well, I'm promising a lot of things. I hope I have time. Okay. So now I got rid of, out of 5, I'm down to 3. And I also know the spin information. And the rest I rely on is very basic fundamental physics, that Kramer's theorem is right, and bands do not stop in the middle of the gap or something. So I have only 2 possibilities. That spin up, this state 1, one possibility is that this band goes up and hits the conduction band. The other possibility, it goes up and it has to hit somewhere. And it must, as I showed, that it has time reversal invariance, it must meet at M with other, because it has to be degenerate there. And as I showed that just by doping the surface, you can get rid of the 2 states because they're trivial. So I'm left with these 2 options. And another option is just put more dopant on the surface and see how much can you go. There is a technical difficulty is that if you dope too much, then your photoemission signal goes down. You cannot see much because you have buried the surface too much.